Assalamu alaikum students. Today we shall continue from the topic which we were doing about the buffers. So basically, buffer was stated as a solution of two components which will try to resist a change in the pH by the externally added acids or bases. Now we'll see about the actions of the acidic buffer, and first we will define what the acidic buffer is. So an acidic buffer solution is such a type of solution which contains a weak acid with the solution of the salt of the acid. So you will have the weak acid and the salt of the acid. It can be generalized as HA. This HA indicates a weak acid, and when it dissociates, it produces the hydrogen ions and the N9 ions. So this is the dissociation of the weak acid. And the salt of this weak acid is represented as the sodium salt of the anions, the same anions which are produced from the HA. So the salt of this anion ion is dissociated completely into the sodium ions and into the anionic ions. So these are the two components, the weak acid and the salt of the weak acid. It's also called as a conjugate base because this is the conjugate base of the acid. Now this buffer solution contains a large amount of the HA which is undissociated. You know that this is a weak acid. That means it will not be completely dissociated into the ions. That's why we see the equilibrium symbol and equilibrium arrow over here. This is the equilibrium arrow. And the salt of this weak acid contains the irreversible arrow. That means there is a complete dissociation of this salt of uh, the salt of this weak acid into the corresponding ions, the sodium ions and the anions. And there will be a very small amount of the hydrogen ions and anionic ions from the dissociation of the acid. So if it is mostly in the undissociated form, then definitely there will be less amount of the hydrogen ions and the anionic ions coming from the HA. This amount will be less from the HA, but the same A negative ion will be greater. It is greater amount because of the complete dissociation of the Na and double A. And there is a large amount of the anionic ions from the fully dissociated salt. This is what it indicates because it is a strong electrolyte. Now, what will happen if we add strong acid into the acidic buffer? We have already said that acidic buffer or basic buffer, they will act against the externally added acid. So if you are adding strong acid into the acidic buffer, then it means, let's suppose I will say you are adding the HCl. You are adding the HCl into the solution, then as a result of this acid dissociation in water, it will produce the hydrogen ions completely along with the chloride ions. These two things will be produced. Now this hydrogen ions will now try to react with the buffer solution. Now within the buffer solution, the prime function of the buffer is to resist the change in the pH, which means that buffer will now come into play and it will react against the added hydrogen ions. Now this is a hydrogen ion which is coming from the HCl, which I have mentioned over there. The same HCl which produce the hydrogen ion, this is the same as hydrogen ion. Now this hydrogen ion is reacting with the A negative ion. Now from where this A negative ion is coming? This A negative ion is coming from the dissociation of the NAA. This NAA, when converted into the sodium ions and A negative ion, this is the same anion over here. I will show this is the same anion coming from the dissociation of the NAA. So when they are reacting with the hydrogen ions of this site, they are these hydrogen are coming from the HCl. What they will do, they will make the HA. Now this HA is basically the same weak acid, this one. So what we have done, we have used our buffer solution in which the anions coming from the NAA reacted with the hydrogen ions which was produced by the HCl, and as a result of this there is a formation of the weak acid which is mostly in the undissociated form. That means the addition of the HCl is not more affected. It becomes another way, it becomes the weak acid HA, and you already know the pH value for the weak acid remains almost a constant. So we have used our acidic buffer to maintain the pH of the solution. If let's suppose there was no buffer solution in any compound, in any system, if there was no buffer solution, then what would happen? By adding this HCl into the solution, there will be an amount of increasing hydrogen ions, and you already familiar that when we have more amount of the hydrogen ions, then the pH of such a system becomes very smaller and smaller. So the pH of such solution would be smaller if there was no if we do not have any buffer solution in the system. But since we do have a buffer solution made by these two components, they have now started reacting against the externally added acid, and this one was a strong acid because the purpose of the buffer is to react against the strong acids or strong bases. So what do we have here? The equilibrium position favors the formation of the unassociated acid, which is the HA. The hydrogen ions are added to the buffer solution. The impact of this change is that there is an increase in the number of the moles of the unassociated acid formed. So addition of the hydrogen ions from the HCl will has reacted with the A negative ion coming from the salt of the weak acid, and they form the weak base. They form the weak acid HA, which is undissociated mostly. And the moles of A negative ion decreases by the amount that reacted with the added hydrogen ions. And these A negative ions were decreased in amount because they have to be reacted with the hydrogen ions coming from the externally added strong acid. Now there is one particular example of this. This information is taken from the other resource book. This says that if you have a weak acid, ethanoic, then what happens? It will split into the hydrogen ions and ethanoate ions. Now, this is the dissociation of a weak acid. Now, if you add an increase in the hydrogen ions would concentration would greatly lower the pH of water, but when hydrogen ions are added to the buffer solution, now these hydrogen ions are coming from the HCl. You are adding HCl into the solution. Now these hydrogen ions are basically reacting with the ethanoate ions, which are coming from the conjugate base. The addition of hydrogen ions shift the position of the equilibrium to the left because the hydrogen ions combine with the ethanoate ions to form more ethanoic acid until equilibrium is re-established. And where these ethanoates are coming mostly, these ethanoates are coming mostly from the concentrations of the sodium ethanoate. I will write here CH3 COONA. When it dissociates, it forms large reserves of ethanoate ions in aqueous form plus sodium ions. Now these are the large reserve of the ethanoate ion which is reacting with the hydrogen ions over here. So the pH does not change significantly. Now what happens? Those ethanoate ions, these will react with the hydrogen ions of the HCl. These hydrogen ions react with the ethanoate ions, and as a result of this, you will have the formation of ethanoic acid again, CH3 COO negative plus hydrogen ions. They form the ethanoic acid, CH3 COOH, and that's a weak acid. So this is how the buffer has played its role to react or counteract with the added HCl. There is another similar information from the third resource book, and they are conveying the same information, the same idea which we have already discussed. You can go through this information by yourself. One thing important over here, no buffer solution can cope with the excessive addition of the acids or alkalis. As we stated before, the previous class, that the buffer solution cannot resist the pH whenever there will be an excessive amount of the added acid or alkali. It can only play its role in a limited range or limit, in a limited range. If very large amounts of acids or alkali are added, the pH will change significantly. So which means the capacity of the pH will exhaust. When the capacity of the buffer solution will exhaust, it will no longer be able to resist the change in the pH. Now the second action. The second action by the acidic buffer is against the added strong base. Now in this situation, you will add a strong base by yourself, and you will see how the buffer will now try to resist the change in the pH. So in this case, I will take an example of the NaOH. It's a strong base. This NaOH, when dissolved in water, it will produce complete sodium ions in aqueous form and complete hydroxide ions in the aqueous form. Now, as a result of added NaOH, there will be a lot of amount of the hydroxide ion present in the solution. How would we neutralize those hydroxide ions? For this purpose, the weak acid will come into play. We remember that weak acid was basically dissociated into hydrogen ions and A negative ions. Although there is a very less amount provided by the buffers by the weak acid, although the amount of H ions is very small, but the thing is that the same hydrogen ions are now playing their role by reacting with the hydroxide ion coming from the NaOH. So I will link this again. This OH negative ion is the same which is mentioned over here. These are the same hydroxide ions. So these these hydroxide are reacting with the hydrogen ions coming from the dissociation of the weak acid. And as a result of this, you know that it's simply a neutralization reaction in which we have the formation of water. So a water has been formed by the neutralization reaction between the two. Removing the hydrogen ions, okay, now what happens when these two have reacted with each other, there will be amount of the hydrogen ions consumed. When it is consumed, then it means that hydrogen ions on the product side has decreased. So according to Le-Chatelier's principle, it states that the equilibrium will tend to oppose that change. So it means if the amount of the hydrogen ion has reduced, then the equilibrium will shift towards the right side, and it will keep on producing more and more hydrogen ions. Those increased amount of the hydrogen ions will again react with the hydroxide ions coming from the strong base. So this will This will maintain the pH. Why? How the pH is maintained? Because the formation of this H2O is simply a neutral thing. H2O has pH value of 7. So this is how the pH of the solution has been protected. It has been neutralized, or you could say it is maintained. The pH of the solution has been maintained by producing the water amount, by producing the water molecule by the reaction of hydrogen ion with the hydroxide ion. So the overall effect is that a decrease in the moles of the undissociated acid formed, since if hydrogen ions are decreasing by the reaction of the hydroxide ion, then Ha will move towards the right side, and as a result of this, Ha will also decrease in amount. This is what it says: a decrease in the moles of undissociated Ha, an increase in the moles of the A negative ions. And A negative ions, these ones, since the direction is moving towards the product side, so it will replenish the amount of the lost hydrogen ion, and also the lost, although it's not lost, but still it will be produced. The same information from the other source book, but it says that an increase in the hydroxide ion solution would greatly increase the pH of the water, but when hydroxide ions are added to the buffer solution, the added hydroxide ion combined with the hydrogen ions to form water, and these hydrogen ions were produced by the weak acid. Ha is the weak acid here. This reduces the hydrogen ions concentration. The position of equilibrium shifts towards the right. This is the same equilibrium which we saw here. It shifted towards the right side. This one, Ha shifted towards the right side. So ethanoic acid molecules ionize to produce more hydrogen ions and more ethanoate ions until equilibrium is reestablished. So if you consider the example weak acid, although I always write H is a weak acid, but if you consider CH3 COOH as a weak acid, then there will be constant dissociation of this ethanoic acid into the ethanoate ion and hydrogen ions. And these are the hydrogen ions which are reacting with the OH negative ions coming from the, I will write that these are the hydrogen ions which will be reacting with the hydroxide ions, and these hydroxide ions were coming from the NaOH and were dissociated into Na plus hydroxide ion. So these are the same hydroxide ion coming from the OH, and as a result of this, there is a formation of the water, which is a neutral compound. So at the end, the pH does not change significantly. This is the reason because there was the formation of the water. Now the next part is the basic buffer. We already defined the basic buffer at the start of the buffer solution topic. A basic buffer is basically a compound in which we have a weak base with a solution of the salt or the base. That means the conjugate acid. We can write it as conjugate acid, or you could write the salt or the base. Now the example included is the ammonia, which is a weak base. WB means weak base. And the conjugate acid of this ammonia is NH4Cl. This is the conjugate acid of the ammonia. Why is it conjugate acid? Because we are constantly saying that when ammonia is dissolved in water, you get ammonium ion, and the same ammonium ion is being produced by the NH4Cl. So this is considered as a conjugate acid of the ammonia. This is a conjugate acid coming from the ammonia. So that's also conjugate acid. And you could write this one as a salt of the weak base. So this is salt of weak base. This is salt of weak base which produces a conjugate acid. So you have both ways to write it. Either you will write the salt of the weak base with the weak base, or you could write conjugate acid of the weak base. Anyways, after we have decided which two components must be used for the buffer solution, we will now see how they are dissociating. The weak base is dissociating into the respective ions, ammonium ions and hydroxide ions, and also the salt of this weak base is dissociating into the ammonium ions and the chloride ions. Now, how they will come into an action, we have to see the same working of the buffer with the added hydrogen ions, or you could say the added acid, and also with the added base. So let's suppose if you add the acid externally, I will again take the example of HCl. This is a strong acid which you are adding into the buffer solution, but this time the buffer is of the basic type. It's not the acidic. Now, when the buffer is the basic type, then according to the equation, this HCl, as we know, it produces the hydrogen ions and chloride ions, and the basic buffer which we produced here, this basic buffer had the hydroxide ions present here. Although they are less in amount because we have the equilibrium arrow over here, but this hydroxide ion is the same one mentioned here, coming from the weak base, and this hydrogen ion is coming from the externally added hydrogen ions. This HCl produced the hydrogen ions, and this is the same hydrogen ion. They are coming from here. When these two are reacting with each other, you will again get the water. So a water has been formed here. Now this water formation has now maintained the pH of the solution. The pH is now maintained over here. So this is one way to understand about the action of the basic buffer with the added acid. There is another way from the other source book. Buffer solution that resists the change in the pH in alkaline solution. The same topic from the other source book, we have similar equation. The weak base added into the water produce the hydroxide ion, and the salt of the weak base produce the ammonium ions and the chloride ions. So this is just an example of the formation of the weak basic buffer. And now the next one is the action of the basic buffer against the strong base. Since we are discussing both the acidic and basic buffer against the acid and the base. Now the last point is the action of the basic buffer against a strong base. Now here, I will again take NaOH as a strong base. When it dissociates in water, it will produce a sodium ion and the hydroxide ions. This will be the formation of the ions from the base. And from the basic buffer, we had the formation of the ammonium ions. The salt of the weak base produced these ammonium ions. Now the same ammonium ions will come over here to react with the hydroxide ions coming from the NaOH. So the strong base produce the hydroxide ions, and the salt of the weak base producing the ammonium ions. They will react with each other, and as a result of this, there will be the formation of, definitely it's a water having a neutral solution, and the other part or the other product is the weak base. And you know that the pH of the weak base is already maintained because we already have the ammonia in the solution, which was used for the formation of the basic buffer. So ammonia is produced back, and the if you think that it has increased the amount of the ammonia, then you should remember it's a weak base. So there will be no effect on the pH of the solution because of the formation of the weak base. There is small equation mentioned here. Write equations to show how the buffer solutions described above removes the added hydrogen ions and added hydroxide ions. They have not cleared which buffer solution, but you should remember if you are adding the acid, then it means it said added hydrogen ions, which means you are adding the acid. So this is the one which you have added. It has to be neutralized by the anions over here. It says it indicates that this would be the acidic buffer. This is an acidic buffer because within the acidic buffer we have the formation of the anions. If you look at here, in the basic buffer, it was the hydroxide ion that was neutralizing the hydrogen ion. It was not the acidic buffer. It is a basic buffer in which the hydroxide ion was reacting with the added acid, which means we are using the acidic buffer here. So this is an acidic buffer which produce the anions. Those anions were reacting with the hydrogen ions of the added one. And if you add the hydroxide ion, then within the acidic buffer, it was the weak acid that was being reacting with the hydroxide ion. So weak acid reacts with the hydroxide ion, and you will get the anions again along with the water formation. So this is the role of the acidic buffer against the added hydrogen ions and added hydroxide ions. So this was all for the today, students. We will continue our lecture from here onwards, and we will see the calculations of the buffer solutions in different ways. Till our next class, take care and Allah Hafiz everyone.